Hey everyone, I just wanted to quickly talk about batteries and electric motive force, so EMF. So we've learned a little bit about capacitors. So capacitors store charge in a circuit. Now capacitors, once you connect it to a circuit, they're going to dissipate that charge quickly. Those charges are going to move away off the capacitor and into the other parts of the circuit. What's nice about batteries, so capacitors discharge charge quickly, whereas batteries are going to be a source of constant, essentially a force. So they're going to be a constant source of charge. So these charges are going to be kept in motion through a circuit if we use a battery. So batteries can be thought of as a charge escalator. So what's going to happen is basically batteries are a source of potential difference. Right? So when positive charges leave the battery, remember when we talk about current, we're talking about conventional current. So it's the flow of positive charges, even though they don't actually flow. But the positive charges leave the positive terminal and then go to the negative terminal. When they leave the positive terminal, they have potential energy. That's actually going to be equal to Q, which is the value of the charge, right? So the charge of an electron, the magnitude of the charge of an electron, times the potential difference of the battery. And when they leave the battery, they're going to they're going to lose energy. They're going to lose energy either through the wire, if we're dealing with a non-idealized wire, as well as through whatever circuit elements we have in the circuit. Whatever element that if it uses power, it's going to cause our potential difference to decrease, and it also means that these charges are going to be losing energy. And when they get to the negative terminal of the battery, they're going to have a potential of 0. Also, actually, what's going to be really helpful when solving circuits or dealing with circuits is to realize that the electric potential of a battery, let's say this was in this example here in this image, say it was a AA or AAA battery, so it's 1.5 volts. The electric potential difference at the positive terminal of the battery is going to be that 1.5 volts, and at the negative end of the battery, that's going to be 0 volts. So the battery, through chemical processes, is actually going to give these charges energy and basically pushes them and forces them through the circuit again. So usually when we dealt with potential energy, or one common form of potential energy is gravitational potential energy. We can kind of have an analogy here to gravitational potential energy. So here on this previous slide, if you think of the battery as a charge escalator, these positive charges are elevated to this higher potential, kind of like gravitational potential energy. The higher you are away from the ground, the more potential energy that object has. Right? So as the charge moves through the circuit, it's going to lose this potential energy as it kind of flows down this circuit. So kind of downhill to the wire until it reaches that negative terminal. The flow of charges is in a continuous loop. We call this a complete circuit. Now, because these batteries actively separate charges, we call a battery a source of EMF, or electromotive force. The symbol for EMF is the Greek letter epsilon. It's a curly E, curly capital E. That's what EMF is. Now, a capacitor stores charge and separated the charges, but it doesn't have a means to do this separation. Right? It's not able to actively separate these charges, where the battery does this through chemical processes. Right? So a charged capacitor has potential difference, but it's not an EMF source. And so batteries are EMF because they actively move the charges, whereas capacitors just store charge. Capacitors just store charge. So I also want to mention, if we have a battery and there's no current running through the battery, its potential difference of the battery is going to be equal to its EMF. right? So you can kind of think of EMF as the idealized potential difference of the battery. So if the battery says it's 1.5 volts, then ideally its EMF is 1.5 volts, right? So a lot of times in circuits, we'll be dealing with this EMF, idealized EMF. In reality, when there's a current running through a wire, the EMF is actually going to be slightly less than its actual EMF, but we're not going to worry about that at all, and AP should not test you on that. The one thing that they may test you on, we'll actually talk about on the next slide. So for the most part, we'll assume that the potential difference of the battery is going to be equal to the EMF. The only time in which this would not be the case that you guys have to worry about is if the battery has an internal resistance. How to decide if a problem you have to worry about the internal resistance of the battery or not? The problem should make it pretty obvious. So either mention that the battery has internal resistance, or it'll be implied in the problem. Okay? Otherwise, we'll be assuming that the battery is idealized, and our change in potential, or potential difference, is going to be the EMF. If our battery does have internal resistance, we might have to actually calculate this internal resistance. We do this through basically an idea called terminal voltage. And what terminal voltage is the actual potential difference provided to the circuit. So say we had that AA battery, 1.5 volts. Its ideal EMF is 1.5 volts, right? So its EMF is 1.5 volts. But because it has internal resistance, we're actually going to lose that potential, so a little bit of that potential difference. So in order to account for that, this terminal voltage, which is the actual voltage that the battery produces, or the actual potential difference the battery has, is going to be the EMF, so whatever the battery ideally has, minus the current multiplied by the internal resistance of the battery. So remember, from Ohm's law, V is equal to I times R. So this is basically just subtracting that potential difference that the battery uses because of its internal resistance is basically what this amounts to. So if you need to calculate the terminal voltage of a battery, or the internal resistance of a battery, or maybe you have the maybe you have the terminal voltage and you want to calculate the battery's EMF, this is basically the formula you're going to use. I do not believe this is on the AP formula sheet, but this is probably useful to know. I'm not saying memorize it, but I'm saying it should make sense, this formula, to you, because this epsilon here is the idealized voltage what the battery should produce, and this is subtracting the amount of voltage that the battery is using up because of internal resistance. And so the net of that is going to be what the battery actually provides, that